Hello student, very good morning to all of you. How are you? I hope you all are happy, healthy and fine at home. Do you remember what were we discussing yesterday? I think yesterday we were discussing about Killeney-Fisher synthesis. Killeney-Fisher synthesis, how the carbohydrates are synthesized by using this method that we were discussing. So today the remaining part of synthesis of carbohydrate that we are going to discuss here. So let us start the Killeney-Fisher synthesis. So this is the one of the excellent method for the synthesis of carbohydrates. Starting from the lower carbohydrate, we can synthesize the higher, means in every step we can increase one carbon atom. How one carbon atom is increased to get the higher carbohydrates, and as we know that carbohydrates are the polyhydroxy aldehyde or ketone is known as carbohydrates. So I think yesterday we have seen, we have taken as a starting material is a triose. Triose is nothing but as a general reference compound we are using is a glyceraldehyde, and glyceraldehyde, diglyceraldehyde. Why it is assigned as a diglyceraldehyde? D and L are the relative configuration, as we know that. So a D configuration, it clearly indicates that the carbohydrate generally represented according to the Fisher projection formula, as we know that. And Fisher projection formula, there are the certain rule to represent that carbohydrates. Rule number 1, the atom, the carbon chain is written or shown vertically with the one oxidizable group at the top. The carbon chain is kept vertically with one oxidizable group at the top. That is rule number 1. Rule number 2, the horizontal bonds are horizontal bonds are considered to be projecting above the plane. That is a rule number 2. And rule number 3, according to that rule number 3, the vertical bonds are considered to be projecting below the plane. So according to that, these are the general way to represent carbohydrate. So yesterday I think we have started as a Killeney-Fisher synthesis. Starting compound we have taken as a glyceraldehyde, and that glyceraldehyde further treated with the hydrogen cyanide. When that hydrogen cyanide react with aldehyde group, it form as a derivative. The name of that derivative is a cyanohydrin derivative, and that cyanohydrin derivative further hydrolyzed by using barium hydroxide, and the compound obtained or the product obtained is known as acid. And once you got the acid, in addition to that, there is a one asymmetric carbon atom is generated. And as we know that asymmetric carbon atom means what? The carbon atom carries 4 different group or 4 different group attached to the carbon atom. That carbon atom is termed as a asymmetric carbon atom. And in every case there is a addition of 1 carbon atom or there is a increase in 1 carbon atom, and we got that. And that acid, if it is further heated, what is going to happen? After heating, the acid and the primary alcohol get reacted together. There is a elimination of water molecule and form as a product. The name of that product is a gamma lactone. If you see there, we are getting as a gamma lactone there. Gamma lactone means the ester group in a cyclic form is known as a lactone. And that lactone, once you got it, and that lactone specifically get reduced with the suitable reducing reagent. The suitable reducing reagent which is used here in this particular Killeney-Fischer synthesis, they have used here sodium amalgam. That sodium amalgam generate the nascent hydrogen which is responsible for the lactone is get converted into as a aldehyde group, and we are getting from triose to tetrose. So in this way we can get this type of the compound. When the hydrogen cyanide treated with that glyceraldehyde, there we are getting as a 2 diastereomeric isomer, which is very important as far as stereochemistry is concerned. And up to that, I think we have obtained the triose, and triose means that tetrose means we are from triose means from glyceraldehyde we have got the glyceraldehyde. As we know that glyceraldehyde mainly present in 2 form. One is they are the enantiomers of each other. Enantiomer means D-glyceraldehyde. Its enantiomer is a L-glyceraldehyde, and the D-glyceraldehyde, D, which clearly indicate that hydroxy group on the right hand side, that molecule is assigned as a D configuration, and whereas when OH group is on the right hand side, first of all the molecule must be written according to as a represented according to as a Fischer projection formula. Then and then you can assign it in a D and L. D means OH group on the right hand side, L configuration means OH group on the right hand side, and that L and D again depends upon the lowest chiral carbon atom, lowest asymmetric carbon atom, means starting from the above top carbon number 1, always given the number to that carbon which is the most oxidizable, means from top to bottom you have to give the number like this. So according to that, from glyceraldehyde, when we are there we are getting D-glyceraldehyde and the L-glyceraldehyde, and when that D-glyceraldehyde treated with hydrogen cyanide, it gives 2 diastereomeric isomer, that is that the derivative which we obtain is a cyanohydrin. 2 cyanohydrin we are getting, 2 diastereomeric cyanohydrin structure we are getting, means there is a generation of 1 chiral center in addition to 1 chiral center present in the glyceraldehyde, another chiral center is generated over there, and that and then we are treating these compound with step by step, with first one with hydrogen cyanide, then hydrolyze it with barium hydroxide, and after the hydrolysis acid we are obtain, and that acid further provide the heat, that acid is get converted into as a lactone, and that lactone particularly or specifically reduced with the sodium amalgam, that get converted into as a aldehyde, and we got the higher carbohydrate, which is nothing but from triose we get as a tetrose, and that is the erythro and the threose which we got over here. So that are the thing we have seen yesterday, that erythros and threose, erythros, L-erythros and L-threose, D-erythros and D-threose which we got. So from that, from erythros and threose, we are going to get remaining part of that, suppose as a D-erythros and the D-threose. Let us consider here D-erythros and D-threose, only D-erythros. Let us consider here D-erythros, D-erythros, and here let us consider here D-threose, right? D-threose, that we are going to consider over here, and these are the tetrose, right? Tetrose means 4 carbon atom there, these all are the tetrose, right? And up to that erythros, starting with that D series we getting over here. Now let us look at here, when this is treated with hydrogen cyanide, then what we can call it as a first one, we treating with that hydrogen cyanide, this is a reagent that form as a cyanohydrin derivative. Second, we are considering that barium hydroxide, OH, twice hydrolysis reaction takes place, that cyanide group is get converted into as acid. Then third one we are using sodium amalgam, not this one, before that we are using just as a heating, there is a elimination of reaction takes place, and fourth one we are using as a sodium amalgam, NaHg, that is a reducing reagent which reduce the gamma lactone into as a particular, what we can call it as a specific aldehyde we got from erythros, glyceraldehyde to the erythros and the threose which we got over here. Now let us see over here what we are going to add here, erythros. These erythros further treated with erythros, and then further treated these erythro, as we know that by adding all these steps together, what you are going to give erythro. Again there are two compound which we are going to get over here, and we know that the structure of erythro, tetrose, structure of erythros, let me draw first the structure of that erythros over here. Erythros, we know that CHO, then here C, then OH, H, then C, OH, H, and then CH2OH. There are two chiral centers are there, and this is the structure of erythros, and the structure of threose. Why it is known as a tetrose? Look at here, number 1, 2, 3 and 4. There are 4 carbon atom, and therefore it is termed as, or it is called as a tetrose. Now here threose again CHO, same thing, but here carbon atom, here the hydroxy group, here hydrogen, the hydroxy group on the left hand side, then C, OH, H, and then CH2OH. That is there, right? So this is called as a D-erythrose. This is known as a D3-ose. Why D3-ose? Remember here, D, the lowest chiral carbon atom over here, lowest asymmetric carbon atom is this one, and here again this one, and let me tell over here, this is the lowest chiral center, and that's what, depending upon that lowest chiral center or the lowest asymmetric center, from that we can designate D or L. Now when adding as a hydrogen cyanide, further followed by barium hydroxide, third reagent heating, and fourth one is a sodium amalgam. If you do all these things over here, there is a increase in one carbon atom, and here when we are adding as a hydrogen cyanide over there, right, hydrogen cyanide, there we are getting two isomeric isomers, diastereomeric isomers, as we know that. And now what is going to happen here, CHOU keep as it is, then in the second this rest of the thing, here we can write as a OH on the right hand side, here hydrogen atom, third, fourth, this 1, 2 and 3 you can keep as it is OH, hydrogen atom and one hydrogen atom, and this CH2OH. This is the compound which we are getting. The name of this compound is a ribose, D-ribose. D, it is depending upon that lowest chiral carbon atom here, hydroxyl group or on the right hand side, therefore it is known as a D-ribose. D-ribose. This is a compound which we got here, D-ribose. Now here what is going to happen here, CHO you keep as it is, but here look at this chiral center over there. This is there are three chiral center, and now when at carbon number 2 hydroxy group on the right hand side, now you can put the hydroxy group on the left hand side here, and they are epimers of each other here, C. Then this other thing, rest of the thing, OH and this carbon OH, rest of the thing remains as it is, then CH2OH. The name of this compound is, there are again as a 3 chiral, but if you see, this is a D-ribose, this is a D-arabinose, D-arabinose. This is the structure of D-arabinose. Now look at here, what I did, when I am adding as a hydrogen cyanide with these erythrose, it produce two diastereomeric isomers, and that's why these are two. Only at this position, carbon number 2, there is a change in configuration. If you see the relationship between this and this, they are what we can call it as a epimers of each other. They are epimers of each other. Epimers means what? Everything is the same, only they differ in the configuration at C2 carbon atom. That type of the compound is known as a epimers. Ribose and the D-arabinose are epimers of each other because they are if you observe this, its absolute configuration at carbon number 2, there you will find one will show the R configuration and one will show the S configuration, and rest of the chiral center, there are the 3 chiral centers, and as we know that depending upon as a chiral center, that also playing as a very important role in the carbohydrate, depending upon as we know that the formula for isomer 2 raised to n indicate as a number of isomers of number n indicate as a number of chiral centers. So look at here, in a erythros there are 2 chiral center. If you substitute 2 raised to 2 is equal to 4. So 4 isomer you are going to get. Here 2 we got, one is a ribose and D is a arabinose. These are the 2 isomers of each other which we got, and they are the epimers of each other. Epimer I already explained about that epimer. What do you mean by the epimers? All the chiral center, whatever chiral centers are there, in every center the configuration, relative configuration, absolute configuration are same, but at one center, at carbon number 2, the relative configurations are different. So that type of the isomers are known as epimers. Now understood this one, how we got here a D-ribose and the D-arabinose. Now let us look at here again. Let me draw again over here. Here, this is the structure of D-triose. We can refer as a tetrose. Why tetrose? There are 4 carbon atoms in the carbohydrate, and that's why it is referred as tetrose. Now how many chiral centers are there? 2 chiral centers are there, and this, they are enantiomers of each other. Enantiomer means what? Everything is the same, but their optical rotations are different over there. Or this erythros and triose, you can call it as a epimers, because if you look at here and here, the configuration is the same, but at this chiral center it will show the different absolute configuration, and therefore erythros and triose are also known as epimers of each other. Here just now we have seen D-ribose and D-arabinose, they are epimers of each other. Epimers means what? Everything is the same. If you look at here carbon number 3, 4, here 3, 4, all are the same configuration, but they differ in a configuration at carbon number 2, and therefore this type of the structure are known as epimers of each other. Now look at this one. I am keeping that CHO as it is. Then here, when adding as a hydrogen cyanide form as a cyanohydrin derivative, there are the 2 possibilities. So there is a generation of that new chiral, and so they are producing that chiral center hydroxy group. In one case it is on a right hand side, and in another case it is on the left hand side. Let me draw first one. Here on the right hand side I am putting the hydrogen atom on the left hand. Now I am keeping all these things, this what is that here, hydrogen atom and OH on the right hand side. So ultimately hydrogen atom is over here, and here is a H, then CH2OH. This is known as a D-xylose, right? This is known as a D-xylose. This is the structure of D-xylose, and there are again as a 3 chiral center, as we know that. Now here I am writing again as a CHO as it is, then C. Now in one case I am keeping hydroxy group on the right hand side. Now I am going to put the hydroxy group on the left hand side, the hydrogen atom, and the rest of the rest of the part remains as it is here C. Look at here, hydrogen atom here, one H over there. Now this one OH and this hydrogen atom, the next one is the CH2OH. If you see this one, again there are 3 chiral centers over there, and these 3 chiral center, only at one chiral center there is a absolute configurations are differ, and therefore these 2, one is a D-xylose and second one is a D-lysose. D-lysose lysose is D-xylose and D-lysose are epimers of each other because they differ at only one chiral center, one having R configuration and other having as a L configuration. So that is the difference over there. So when Killeney-Fischer synthesis further continued, we get following 8 isomers of D-aldohexose from D-erythrose and D-threose as follows, which we have seen just now. We got as a D-ribose, D-arabinose, D-xylose and D-lysose. So these are the part we have seen over here. And now the important one, D-ribose, D-arabinose, D-xylose and D. Again further we are going to treat this compound with those and we will get the remaining 8 part. And out of that 16 isomers, if you look at over here, 16 isomers, out of that 16, one will be the, what we can call it as a D-glucose that we are going to see over here. Now let me clean over here ribose. Now ribose will give two structures. D-arabinose give you the 2 structures and D-xylose will give you 2 structures and D-lysose will give you 2 structures. Let us see over here the structures of those things. Let me clean the board first over here and I am going to draw those structures here from. So let us see over here from this D-ribose. Let us see here this D-ribose I am writing over here. D-ribose. Here I am going to get 2 structures like this and D-ribose. After that D-arabinose. D-arabinose and these D-arabinose again produce 2 structures. Then D-xylose. D-xylose will give you 2 structures like this and D-lysose. D-lysose will give you 2 structures. They are like this. So let us see how we are going to get. So it's very easy. We know that D-ribose, right? These structures we are going to add what? First one we are going to add as a hydrogen cyanide. You are going to get as a 2 diastereomeric cyanohydrin derivatives and that derivatives we are going to treat with barium hydroxide, which will give you the cyanide group is get converted into as a acid. When acid and the primary alcohol they come together just by heating, the resulting compound obtained is called as a lactone. And the fourth one, just we are reducing that lactone derivative with the help of sodium amalgam, gives the aldehyde group back with 1 carbon atom increase. So this is called as a step up reaction. Killeney-Fischer synthesis is also known as a step up reaction. And let us see over here how we can arrive. So by doing all these things together, what I am going to get over here, that CHO it remains as it is, right? Now here OH, in first time I am putting that hydrogen side hydroxy group on the right hand side. Here also CHO, look at here, I am going to put as a hydroxy group on the left hand side. So this is the first part. Remember, this one is a very very important part which we are getting by adding all these things, right? So rest of the thing, whatever thing of D-arabinose, they remains as it is. Now start from here, 1, 2 and 3, right? 1, 2 and 3. Now here all these hydroxy group on the right hand side, so write it as it is, hydrogen atom, and this hydrogen atom and CH2OH. It is known as, the name of this compound is known as a D-allose. The name of this compound is a D-allose. The name of this compound is a D-allose, right? Now here also, once you write down as it is 1, 2 and these 3. Let me clean over here so that we finish the work of this. So here, what is there? OH on the right hand side, OH on the right hand side, OH, and then CH2OH. Here hydrogen atom, here hydrogen atom, here hydrogen atom. The name of this compound, 1, 2, 3, 4, 5 and 6. 4 chiral carbon atoms are there. 1, 2, 3, 4 chiral centers are there. 1, 2, 3, 4 and 4 chiral centers are there. And the name of this compound is a D-ultrose. The name of this compound is a D-ultrose. D-ultrose. That the compound which we got over here. Right? And now D-arabinose is very important, because from this we are going to get the D-glucose, which is very abundant in nature in a combined state as well as in a free state, and that's why concentrate over here. So here CHO, I am writing this one as it is, CHO. Then COH I am writing on the right hand side. Then CHO, this part is coming here, hydroxy group on the left hand side. Look at here, this part which is coming from by doing all these steps sequentially, and then we got this one, 2 derivatives, hydrogen cyanide gives OH, and on the right hand side, one on the left hand side. Now rest of the thing, this part you keep as it is, this one, right? This you write down as it is here. C, look at here, HO on left hand side, hydrogen, then OH, then COH, hydrogen atom, this hydrogen atom and this CH2OH. The name of this compound, as we know that, the name of this compound is a D-glucose. The name of this compound is a D-glucose. This one is a D-glucose. D-glucose. This is the name of this compound, D-glucose. How we got D-glucose? Let's see over here. And here, look at this one. Now this part, carbon, carbon and third carbon. Here HO on the left hand side, H, then 2OH are on the right hand side, and therefore this is the structure which we got, and the name of this compound is a D-mannose. D-mannose. The name of this compound is a D-mannose, which we got over here. And now the rest of the thing, after D-mannose, one D-glucose and the D-mannose. Now from D-xylose, remember here D-xylose, this is the structure of D-xylose. As usual, you can write CHO, then C, put hydroxy group on the right hand side. In the second case, you write that hydroxy group on the left hand side. This is a crucial, very crucial step in synthesis of carbohydrate. By doing all this operation together, resulting compound is obtained as a this one, because there is a one extra asymmetric carbon atom is added. Now here the rest of the thing remains as it is, 3 carbon atom, 1, 2 and 3. Look at here, OH, then hydrogen atom and OH here, and CH2OH, here hydrogen atom, here HO, here is a hydrogen atom. The name of this compound is known as D-glucose. The name of this compound is a D-glucose. 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 The name of this structure is a D-glucose. Now here this one we are talking about. Here again 3, 1, 2 and 3. Look at one OH on right hand side, hydrogen atom and this OH, and rest of the thing CH2OH, H. Here you can add H. Here is a OH. Here is a hydrogen atom. 4 chiral center. They are as it is, and the name of this compound is known as a D-iodose. D-iodose. This is a D-iodose. D-iodose, the name of this compound. Now the last one from D-xylose. What we are going to get from D-xylose? Let us consider here this one, right? CHO. Then by doing all these steps, put first one on the right hand side, then H left hand side, then CHO. Again put here the hydroxyl group on the left hand side. That is a main point to discussion, and rest of the thing remains as it is here. 1, 2 and 3 carbon atom. Here hydroxy group on the left hand side, here hydroxy group on the left hand side, here OH, then CH2OH. This rest of the thing you can put the hydrogen atom, and the name of this compound is a D-glucose. 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 D-glucose, that is the name of this compound. And now the rest of the thing here again. 1, 2 and 3 carbon atom, then CH2OH. Here look at, here hydroxy group on the left hand side, another hydroxy group on the left hand side, there OH on the right hand side, H, and here hydrogen atom over there. So look at, there are again as a 4 chiral center. The name of this compound, last one, is a D-talose. The D-talose. So these are the name of this compound. So in this way we have studied the Killeney-Fisher synthesis. How can we can increase the number of carbon atom? Remember, there are the 4, by doing as a 4 step, there is a increase in 1 extra asymmetric carbon atom in that. So by using this one basics that from D-ribose, D-arabinose, D-xylose and D-lysose, let us look at some of the observation. What are the observation or the conclusion drawn from this Killeney-Fisher synthesis? Let us see over here. Number 1, in the above synthesis, it is clear that the final product differ only in the position of OH group at the carbon atom adjacent to the CHO group, and therefore in every cases you will find this is a very important part, because that is going to add in every case by doing this thing. So that is the difference. This is the first observation we have seen over here. Second observation, the configuration of asymmetric carbon atom present originally in glyceraldehyde remains unchanged, whatever D series. So throughout you can see this is the D series, because at the lowest asymmetric carbon atom the hydroxy group are on the right hand side, and therefore it is designated as D configuration. Number 3, the 2 sugar obtained from D plus glyceraldehyde are known as D sugars, D erythros and D threos. Number fourth observation, similarly, two sugars obtained from L minus glyceraldehyde will be called L sugars, and they further on Killian synthesis will give 8 isomers of L aldohexose. And now the fifth observation, the number of optical isomers depends upon the number of asymmetric carbon atoms present in the molecule. The number of optical isomers are given by 2 raised to n. I already told you that 2 raised to n, 2 raised to n, where n is equal to number of asymmetric carbon atoms. Glucose contains 4 asymmetric carbon atoms. Look at here, glucose 1, 2, 3, 4, 5 and 6. So there are 4 chiral centers are there at carbon number 2, carbon number 3 and carbon number 5. So C2, C3, C4, C5, and hence 2 raised to n is equal to 2 raised to 4 is equal to 16 isomers are possible. Out of 16 isomers, 8 isomers belong to D series and remaining 8 isomers belong to L series. And observation number 6, the pair of aldehydes obtained differ only in configuration about C2 and hence are epimers of each other. Epimers, as I already told you, that in all the chiral center, the configurations are same, absolute configurations are same, but at C2 carbon they are differ. One will show the R configuration, another must show the S configuration. I think with this, in the next time we will discuss about the rub degradation, how increase of carbon by Killian-Fischer synthesis, but by decreasing the carbon atom, there is one famous reaction that is called as the rub degradation. So that we will see in the next lecture. Thank you. Let us stop today here. Thank you. Have a nice day.